Okay, so this is the last section in Chapter 8. We are going to continue our discussion about tests about population mean, and in this case, we're actually going to take a look at matched pairs and how that correlates with a one-sample t-test. All right, so by the end of this section, you'll be able to perform a significance test about a mean difference using paired data. All right, so hopefully you remember what paired data was from previous sections when we did experiments. So remember, paired data is usually like a before and an after. So you take your pulse rate and then you drink a bottle of Coke, and then you take your pulse rate after that, and we're going to do a before and after comparison to look at the difference in your pulse rates. We're not specifically looking at the before or the after, we're subtracting them to find the difference in the two. And that's what we're going to take a look at in order to check that's the kind of data we're going to take a look at for paired data. All right, so comparative studies are usually more convincing than single sample investigations. For that reason, one sample inference is less common than comparative inference. So studies designs that involve making two observations on the same individual or one observation on similar individuals results in paired data. So the first one I talked about was the before and after, one observation on two individuals, one observation on the same individual. An observation on two similar individuals would be to take two males of the same height, same weight, same athletic ability, take their pulse rate, and one takes the pulse rate without the Coke, and then the other one takes it after drinking the Coke, and so then we would take the difference in those pulse rates. So there's two different types of paired data. Okay, so here's a couple more examples. So remember that matched pairs is a special case of randomized block design. So matched pairs came from our experimental design. It can be a before and an after. All right, so that's taking your pulse, drinking your Coke, taking your pulse again, or two blocks in one unit. So that's Sam not drinking the Coke and Joe drinking the Coke, and then comparing their two pulse rates. Okay, and then why would we use paired data over single sample data? What it can do, it can increase the power by accounting for a source of variability in the response variable. So when you're doing a before and after, that gets rid of the variability that is between two different people. You're basically the subject, remember, serves as the control in that case. Okay, so when paired data results from measuring the same quantitative variable twice, as in the job satisfaction study, we can make comparisons by analyzing the differences in each pairs. Okay, so here's an example. We could have everyone in the AP Statistics course take the SATs. They could then take a prep class and record the SATs after the scores of the SATs after the prep class. We could then look at the difference in the scores. Were they higher or were they lower? So notice we're still only taking a look at one thing. In the end, we're just taking a look at the difference in the scores. We're taking the scores that we did before, and then we're taking the scores after, subtracting them, and then we're just going to say, okay, what are the differences? How did the differences change? Okay, if we're just comparing the differences, we're only looking at one set of data. So since we're only looking at one set of data, the methods that we use for this test of significance is called a paired T procedure, which is basically the same thing as a one sample T procedure. All right, so you're not really using anything new in this section. We just have a few little things that we're changing with some notations. But if the conditions for inference are met, so that's your simple random sample, 10% condition, and then approximately normal condition, we use a one sample T procedure to perform inference about the mean difference. So that's basically saying we're taking a look at the difference and we're saying, hey, is this difference in the before and the after, is that actually significant? But it's only a one sample because the only thing that we're taking a look at is the differences. Paired T procedures follow the same process as a one sample t-test for means. The one sample you'll be using is the difference. We're always going to do the after minus the before. Okay, because that's going to tell us what the difference is. All right, so just a summary to sort of pull everything together. In a comparative study, we may want to compare two treatments, or we may want to compare two populations. In either case, the samples must be chosen independently and randomly in order to perform statistical inference. Okay, so these are separate. So when we're comparing two different treatments, that's two different populations or two different things. If we're comparing two different populations, those are two independent populations, and that would be a two sample test. But when we're comparing two sets of data from the same population, since it's only one population, it's going to be a matched pairs design because the subjects aren't chosen independently. And when I say they're not chosen independently, each individual is independent, but it's the same population for the before and the after. It's the same students taking the SAT before they take the prep course, and then it's the same students taking the SAT after the prep course. So the populations that do the before and the after are not chosen independently. It's the same thing. Okay, it sort of is two different treatments in the fact that we have no treatment then a treatment, but it's still the same population. So since it's the same population and the populations are independent, we apply the one sample t-test to test the differences in that specific population. Okay, now there's two common types. We're going to do a matched pairs or a before and an after. So matched, that's, remember, when you have two of the exact same people, maybe they have the exact same grades and one took the prep course and one didn't take the prep course, and then we compare those differences. Or the before and the after. Okay, and you always, when you do the difference, always do the after minus the before, because we're checking to see what happens afterwards. The key in knowing that it's matched pairs is that both sets of data is from the same population. So we're using the same population for the before and the after. Okay, so let's just take a look at an example. Researchers designed an experiment to study the effects of caffeine withdrawal. Yikes! They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, cola, and any substance with caffeine for the duration of the experiment. During one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. The order in which the subjects took the caffeine and the placebo was randomized. At the end of each 2-day period, a test for depression was given to all 11 subjects. Okay, so this is still the same populations. This is a matched pairs because it's the same subjects that are taking the caffeine and the same subjects that are getting the placebo. So researchers wanted to know if being deprived of caffeine would lead to an increase in depression at the significance level alpha equals 0.05. All right, so let's take a look. Now, this table below contains the data on the subject scores on a depression test. Okay, the higher scores show more symptoms of depression. So if you're a 0, you're not depressed. If you're a 10, you're really depressed. Okay, maybe 20. All right, so notice how I have the subjects, and I did two things: depression level with caffeine, depression level without caffeine. Now notice here that it's the same subjects, it's the same population I'm using for two different treatments, okay? So here's all the scores with caffeine, how depressed they were, and here's all the scores when they didn't have caffeine. But when you do a matched pairs t-test, we're looking at the difference. We want to say what happens when I do the after minus before. Okay, so I'm going to take these two, I'm going to subtract them, and here's the differences in the after minus before. Since we're checking to see if it made a difference when I did not give them caffeine, we're only going to do a test on the differences. This is the one sample of data that you're going to perform the t-test on. Once you've found the differences, you're just going to literally ignore the rest of the data. You could cross it out if that's helpful for you, so you know that you're only looking at the differences. What happens if I don't give them the caffeine, okay? And just remember that you're always going to do the after minus the before, because the difference is saying, hey, how did the treatment affect what happened? All right, so why did the researchers randomly assign the order in which subjects receive placebo and caffeine? Remember that we need to have random assignment, all right, in order to come up with conclusions. So they wanted to be able to conclude that any statistical significant change in depression is due to the treatments themselves and not to some other variable. All right, so that's helping to control for some of the lurking and the outside variables. Okay, and also just remember that in order to establish cause and effect, we needed to make sure that they randomly assign them. Okay, now one obvious concern is the order of the treatment. Suppose that caffeine was given to all the subjects during the first 2-day period. What if the weather was nicer and on these 2 days than during the second 2-day period when all subjects were given a placebo? Researchers wouldn't be able to tell if there was a large increase in the mean depression score was due to the difference or due to the treatments, because usually if it's sunny out, people are happier, but if it's rainy and dreary, then people are usually a little bit more depressed. So we wouldn't know, hey, is it the fact that they didn't get caffeine or they're just more depressed because the weather is not as nice? Random assignment of the caffeine and the placebo to the 2 time periods in the experiments would also help ensure that no other variable like weather is affecting the subject's responses. All right, so let's carry out a test to investigate the researcher's question. So you're going to carry out this test the same way you did in the last section. So if caffeine depression has no effect on depression, then we would expect the actual mean difference to be 0. So when the difference is 0, that means there was no difference. That basically means the treatment had no effect whatsoever. That's always what we're testing against in a matched pairs test. In a matched pairs test, we're assuming that there is no difference. So remember in the last sections, we always said there was no difference from the null. It was always equal to whatever the population mean or proportion was. In this case, we're saying that the difference is 0. So if the conditions are met, we should use a matched pairs t-test. You can also state that we're using a one sample t-test for means. Same conditions apply here since we're doing means. Researchers randomly assign the treatments. Okay, so this is a little bit different than the other question. So I'm sure the subjects were a simple random sample, but they also randomly assigned the treatments here since we were looking at an experiment specifically in this case. Independence, each volunteer scores are independent of each other. So keep in mind that showing each person is independent of each other, but the 2 populations that did the placebo and did the caffeine, they were not independent, which is what made it a matched pairs. Okay, to check to see if it's approximately normal, since the n is less than 15, we're going to use a histogram and normal probability plot to check. Using one of them is fine. Just make sure you state how you know it's approximately normal. The histogram has an irregular shape, so with a few values, but then in the normal probability plot is slightly curved, indicating some slight skewness, but remember that the T procedures are robust. There's no outliers or strong skewness, so the T procedures should be pretty accurate. So, and when I say that the T procedures are pretty robust, it means that, remember, your T curve has more values in the tail, so it's going to capture the true mean or proportion most of the time. Okay, so let's see what this looks like. Where did the histogram and normal probability plot come from? So we had that graph. Okay, which one did we use? Did we use the placebo? Did we use the caffeine? No. Remember I said cross those out, and once you have those differences, that's literally the only set of data you're going to use. So when you do a histogram and when you do your normal probability plot, they are graphs of the differences. Do not make a plot of the 2 original data sets. That's not what we're testing. We're testing the difference between the 2. Okay, so your normal probability plot is the normal probability plot of the differences, and then your histogram is a histogram of the differences of the after minus the before, not the 2 original sets of data. Okay. All right, now let's just take a look at the null and alternative. Remember I said that we're assuming the null is always going to be assuming that there is no difference, so the treatment doesn't make a difference, so that's like saying the difference is equal to 0. It's always going to be the same. That is always going to be the same for matched pairs. Okay, now notice how this says this has a little notation of D here, where in the past we just said the mean was equal to whatever. You want to make sure that's really important that you denote that D there. Well, why? Because that's telling your reader that I took a look at the differences and then I'm comparing the differences. That tells the reader what you're doing, okay? And then the alternative, same thing. All right, it can be less than 0, greater than 0, not equal to 0, but it has the same notation. This tells the reader that we're looking at the differences. The alternative is showing that there's a positive difference. What does that mean? There's an increase. Increase in the depression means the differences will be greater than 0, because we wanted to check and see if we take caffeine away, if the depression increased. Notice how we still have the difference defined. The mu of D is the true mean difference, placebo minus caffeine, after minus before, in depression scores for subjects like these, okay? Now, notice the differences from the orange columns on the previous slide. Once you found the differences, okay, just pretend like the rest of the data does not exist, okay? And I just wanted to show you the difference between what your null looks like, your symbols, and your alternative. One sample mean is mu, matched pairs is mu of D, difference of means.